the physics of the world to produce behavior. And at the end of the day, if that behavior is time varying, then you can understand it as a dynamical system. And so it's a wonderful area, many interesting questions, few answers, but hopefully we can work to get more answers in this area of understanding biological systems and specifically neuromuscular systems from a mathematical framework.
Great. And you're also going to be here on the, is it the optimal control day that you're going to?
Yeah, on Wednesday,
yeah, cool.
I believe, yeah.
Great. Okay, thanks. And then last but not least, Songting.
So hi everyone, I'm Songting Li. I'm currently an assistant professor in the Institute of Natural Sciences at Shanghai Jiaotong. It's in Shanghai, China. And my lab is interested in using mathematical and physical approaches to understand the brain dynamics across multiple scales, like from single neuron to networks. And for single neuron, we are particularly interested in how a neuron integrates synaptic inputs from the dendrites, the process known as dendritic integration or synaptic integration. And also, we are curious about what computations can a single neuron perform by taking advantage of its passive cable property or this active ion channel dynamics. And for network, we're interested in studying how the realistic structural connectivity affects neural dynamics. We know that the connectivity between neurons or brain areas are not random. So how that shapes the network dynamics is our another interest. And also, we're interested in developing some nonlinear causal inference methods, trying to link the structural connectivity and functional connectivity. So in short, I'm actually working on nonlinear systems. But I think it's good to discuss linear system here because many nonlinear systems can be well approximated by linear system or descriptions. So, yeah.
I think that was one of the points that Bing made in some of her lectures today, which was always start with linear. You can always make it more complicated. Okay, great. So before we go too much farther into the Q&A, because we don't have too many questions yet also, but what I would like to do first is remind everybody, please, can you see my screen? I think so. So please do your reflections. If you haven't done these in a little while, just to remind you, this is telling us how you are feeling about today's material, but also how you're feeling about your pod dynamics and so on. So this is really important, not just for us, but also for you guys to really think about what you got out of today, to try to connect it to your previous knowledge and your previous understanding. So please go do this, and we'll give you a couple minutes to do this. And then also while you're doing this and you're thinking about what you came up with today and what answers you gained, but also what questions you developed over the course of today. Type those into the Q&A box too, so we can talk about some of those insights that you guys came to, or some of your still kind of open questions about the concepts that we talked about today. So I'm going to leave this up here on the screen for a little bit. And for now, we can just take a couple minutes and sit back and relax while the students do these. So please do these, guys. And I will also post the links in the chat as well to make it easy. We've got some nice praise in the chat for Bing as well. Your explanations were phenomenal.
Thank you.
So that's great. Yeah. So please, put stuff in the reflections too about what you liked or what you didn't like in the tutorials. And if you want to add that stuff into the text box, the comments box, that's also really helpful. Helps you guys think as well. So I'm going to take this down now while you guys are finishing this out, but please do continue to do them. And what we can do now is we actually have a couple questions that we can get started on. But before we do that, and I'm kind of putting you guys on the spot here, but I thought maybe if there was a a favorite example that you guys have of how you might use some of these types of systems in your own research, or something similar even, that we could do a little bit of a roundtable to kind of demonstrate the diversity of how we all use this in our own research. And again, I'm putting you on the spot, but you know, we can I think go around the table. So does anyone want to go first?
For this particular question about
Oh no, just for like dynamical systems in general,
Mm.
or linear dynamical systems, or even some of the topics that got touched on in like the intro or the discussion today. And if you didn't watch the videos, then that's cool. We can also talk about just linear dynamic systems in general.
This is not for my own research, but we were really glad to have gotten Krishna Shenoy to give the outro video today, because I think his research in terms of explaining the population activity of motor neurons in the monkey cortex is some of the most beautiful work I've seen, really applying linear dynamical systems to explain neuroactivity. So I was really happy that he gave that beautiful lecture. I hope many of you have gotten a chance to watch it. In my own work, there's a line of work we've been doing to model high electrode count human electrocorticography. And so it ends up just being really long time series data of many, many, many electrodes, kind of like LFP, local field potentials. And they are most certainly not linear. I think that was one of the questions that came up. I'm sorry, I'm gonna jump and just read from the question. Are there any brain functions that can only be explained by nonlinear dynamical systems equations? The snarky answer is yes, all of them. You kind of need nonlinear dynamical systems to explain all of them. However, if you look closely enough, especially over a short window, things tend to look pretty linear, and linear systems work remarkably well. And so that's what we did with the human ECOG reportings. We looked over short windows and modeled it as a moving window of linear dynamical systems. And so you can do it as switching linear dynamical systems or smoothly varying linear dynamical systems. And the mathematics gets a lot easier, and things work really well without having to evoke a lot of nonlinear theory. And so that's something that we've done a lot.
Cool, thanks. Francisco or Songting, do you want to have a favorite anecdote?
Well, I think one thing, if you're interested in this field, you should definitely study manifold theory, because manifold theory essentially describes the high dimensional evolution of processes. And the process typically evolves not in the entire space, but rather it follows a lower dimensional structure.
Mm-hmm.
If it were a high dimensional process that is always visiting every dimension of the space, you just essentially have randomness. That's not the case. As soon as there is some structure to the behavior, it will collapse to a lower dimensional subspace. And those lower dimensional subspaces can be very complicated, but the definition of a manifold is that it's locally Euclidean, meaning there is always a small enough patch that can be approximated as a flat plane or hyperplane. So that's why a lot of people make a lot of debates about, is it linear, is it nonlinear? Well, the answer is yes. It's both nonlinear, but if you choose your coordinates carefully, you could see it as linear for a little while. Then people get into, lots of unnecessary debates about it's strictly linear or it's all nonlinear. Well, if that patch gets bigger, you're going to start picking out the non-Euclidean features, and then sure, you cannot use linear methods anymore. So my advice to you is to be careful not to want a simple answer. The answer comes from the scope, either spatial or temporal, that you're interested in and for which you have questions. Don't get hung up on, is it linear, is it nonlinear? The answer is yes.
I think that's actually really nice, because one of the last things that we did last week was dimensionality reduction, and we talked about manifolds, and we talked about lower dimensional spaces, and spent a good deal of time on PCA. And later in the course, we're also going to learn about autoencoders as a process, or a way of doing kind of assumption-free dimensionality reduction. And so all of these kind of fit together, and that like if you make the space small enough or low dimensional enough or simple enough, then linearity works. And that's great because it's very handy mathematically to do it that way. Cool. And Songting, do you have a favorite story?
Yeah, sure. So when I teach mathematics, I always use this, my favorite example, this 2D linear system, because it has very simple structure, right? For example, this Wilson-Cohen, I actually made the tutorial next week about this Wilson-Cohen one, because it has rich dynamics. You can have fixed points, and also you have a limit circle doing oscillation. And importantly, you can actually view it, on the plane. So you can have a very full and intuitive understanding about the system. Once you get to know that system well, it will be easy for you to generalize to understand the higher dimension system. Because many students complain that linear system or linear algebra actually is very difficult. That is because the dimension goes, once dimension goes high, then it's very hard for you to imagine what's going on in the system. You can even become very difficult to identify it is a linear system. Once you know this low dimensional case, then it will be much more helpful for you to understand this kind of system. Yeah.
So do you mean to say that if you get good enough at doing these kinds of models, that you can just run these linear systems in your head, you can run the simulations in your head, and like you don't need to actually simulate them on a computer anymore?
Oh, no, I mean, so once you get to know the properties of linear system in 2D, then it will help you to understand the linear system in high D.
Yeah.
Yeah.
Yeah, I still have trouble, thinking about some of these dynamical systems just in 2D as well. It's not it's not a trivial thing to do. But the more you kind of get to know these systems, the better you are at kind of getting an intuitive grasp. Cool. So we have just a couple questions here, but I want to remind you guys that the Zoom interface, the Zoom webinar interface, is actually a lot like Crowdcast. So it's a lot like what we've been using before. It just looks a little different. So you've got a chat box, which will be down at the bottom of your screen. And so you can chat there. You've got an attendees box where you can maybe see who else is here. And you've also got at the bottom of your screen a Q&A box. And so this is just like the one that's in Crowdcast, where you can put up your questions and you can actually vote on other people's questions as well. So please ask your questions and so we can have a fun discussion here. I'll just say like a couple words. Again, linear systems and dynamical systems are not a large part of what I do in my research, but we have been using them a little bit. And I was glad to see in the intro video that the 2001 paper by Usher and McClelland made an appearance, the leaky computing accumulator, because that one has actually been very inspirational in some of the stuff that we're working on right now, where you talked about how if W, which is the weight of the inhibition in between the two units, whether that's big or small, kind of changes how the system behaves. So I think that simulating some of these things where you can actually simulate like a leaky computing accumulator, and you can get a handle on how mutual inhibition or lack of mutual inhibition changes how the system interacts with itself. It's one of my favorite things to kind of teach, is like a very basic, is there inhibition or not in terms of an accumulation system. So these are all really great tools, and you can use them to do all sorts of different things, for everything from decision making to understanding like real neurons behavior. Cool. Okay, so there was okay, so now we've got a couple questions here. Let me just make sure that that we didn't miss one here. So there is one that's marked as answered, and I don't think this is exactly exactly what we were answering before. So let me just grab this one before it goes out of our brains, which is, could you please clarify how we determine whether a system is stable or unstable? And so maybe this is referring to whether A is positive or negative or zero in some of the tutorials. So I don't know if I'm kind of shunting this towards you, Bing, but if other people want to jump in too, then that's also fine. Can we talk a little bit about this just to get everybody on the same page and make sure that we're all all on the same foundation?
Yeah, for sure. I'm also guessing that it's referring to some of the behaviors that we worked over in the tutorials. And I know that this was actually one of the more confusing parts of today's tutorials, because we did both the continuous time formulation as well as the discrete time formulation of these linear dynamical systems. So all of us content creators for this week, we actually had a small discussion about whether or not we wanted to stick with one instead of just doing both. And there was a lot of, because it confuses, like every time I teach this, some students get confused. So it is confusing. I acknowledge that this is a confusing thing. It confuses my students, my grad students too. But I tried to lay it out as clearly as I could. But I get that it's a confusing thing. So I'm gonna guess that you mean that given an A matrix, how do you tell if a system is stable or unstable? I don't know if that's the question you're asking or not, but I'm guessing that that might be what you're asking. And if that's the question you're asking, okay, great. Thank you, Sophia, for clarifying, especially thinking about the stream plots at the end of tutorial 1. Yeah, absolutely. So in the stream plots, we were looking at a two-dimensional continuous time dynamical system. So it's x dot equals ax, where A is a 2x2 matrix. Songting, I don't know if this is the type of toy example that you do in your math classes sometimes, but it's a very common one. Like we all took this class, right? Like we had to do a lot of those A matrices. And so when you have a two-dimensional linear dynamical system of the form x dot equals ax, there's always something happening around the origin. The action is always around the origin, right? And so there's only so many things that can happen, and you could have the origin be a source where all of the arrows are pointing out, right? So the system is going to be growing. You can have it be a sink where all of the action is coming in, right? It could do that while it's swirling if you have an imaginary component to the eigenvalues of the A matrix. So those are things that can happen. You can have what's called a stable orbit, a stable periodic orbit where things are going in circles. Those are really useful for modeling cyclic behaviors like bursting neurons, or people use them a lot for modeling walking, for example, because it's a really cyclic behavior. Or you can have what's called a saddle, where it's stable in one direction and unstable in the opposite direction, like the shape of a horse saddle or a Pringle potato chip, if you kind of can picture what that looks like. And that's it. Like that's all that can all really happen. That's all that can happen in this restricted linear system, which is why we can kind of enumerate them all in a short tutorial like we did today. Is that kind of what you're asking? I hope.
I mean, that sounds maybe to me like it's a relatively very comprehensive explanation. And so Sophia and Juan are following up on this. I think we want to, yeah, perfect. Okay, so great. So let's, I want to save some of the details about the tutorials for later, mostly because Bing is the author of the wonderful tutorials today, but we're all here and we've got some kind of other fun conceptual things to talk about. So Juan, hold that thought and maybe we'll come back to it at the end, okay? All right, cool. So there's a couple other questions that we have here, and I actually really like the top one, which is from Swimming Pod 50. I'm not sure who that is, but Swimming Pod 50 asks, when applying dynamic systems and dimensionality reduction, which was first introduced by Byron Yu back in week 1, day 5, when we talked about dimensionality reduction and manifolds and so on. Are there any differences in mechanisms between individuals? In other words, how do we reach conclusions across subjects? So this is kind of an interesting question to me. I wonder if any of you wants to jump in and answer.
I'd like to touch upon that because I've written a couple of papers on the subject, and essentially this goes back to a very critical experimental decision people had to make when writing a doctoral dissertation, which was, I can do some experiments, I can record from some people. And so the question is, should I make my model subject specific or should I make my model generic?
Mhm.
And all through the 70s, 80s, and 90s, most of the dissertation work and therefore publications was, this is a generic model, and there were fabulous examples from Aaron McNeil Alexander, for example. He would have very simple mathematical models that were generic, that would apply to all quadrupeds, or to all bipeds, or to all locomotor behavior, versus people were saying, no, if you want to model a gazelle, you need to get the gazelle to the detail of the gazelle. Otherwise, you cannot answer gazelle questions. But this is actually a false choice, because in a paper with Veronica Santos, who's now faculty at UCLA, and other papers in my work, what you want to do with a model or a mathematical description of something is just find out what the range of predictions are. And often the range of predictions are not just a Gaussian distribution. They actually tend to be multimodal, such that it's not that there is one kind of person, and so are you like the mean person, or like the average person, or are you an outlier? It actually turns out that there are several kinds of people, there's several kinds of behavior. Clinically, you can ask people, are they either responders or non-responders? It's not like they're all part of the same continuum. So you should look at multimodal distributions. And I don't know, Megan, if you've pointed people to literature. For example, people can look at my book, which is available for free under Moscow Systems, and talk about that. So I'm afraid that oftentimes people get caught up into the question, is this linear or nonlinear? I need an answer. Tell me yes or no, like the question about brain functions, are they exclusively nonlinear? Or people ask the question, is this a general solution, or is this a specific solution to this species, to this behavior? But you need to sort of open your eyes to the continuum of explanations, right? And I suggested in the chat window a must-read book by Steve Strogatz, which is Nonlinear Dynamics and Chaos. And in that introduction, he makes an excellent case. Just because you're taught linear systems first doesn't mean that you first have things are either linear or nonlinear. You should read that book, definitely. I don't know if this is a long-winded answer to that question, but oftentimes people get stuck on like, must you have a generic model? Must you have a specific model? You need to be open to kind of more possibilities.
If I may add on to that answer, specifically to Swimming Pod 50's question about comparing among individuals. A couple of things come to mind in terms of the best examples that I've seen recently of really excellent work along those lines. One of them is a theoretical and an experimental result that came out of the Miller Lab. They also worked, they're a theoretical and computational collaborator with Sarah Soya. And what they did was examine the population neural activity in motor neurons in monkeys doing the same task over months to years. So it's not among different individuals, but it's among the same individuals over many, many long periods of time. And what they were able to show is that Francisco mentioned manifolds earlier, right? So that there is these neural manifolds, and though they change a little bit over time, they had the same structure over many, many months, which is a really wonderful and remarkable result. Along those same lines, there's a related result by Ava Dyer, who is at Georgia Tech. So what she showed is that if you do the same manifold reduction analysis for neural activity over multiple monkeys now, doing similar tasks, you'll see that they come out with different manifolds, right? But you can basically do an alignment. You can do I know my hands don't actually align. Imagine there's a mirror. So you're allowed to like do mirrors and rotations and stretching and stuff. You can get them to lie on top of each other which is also kind of remarkable, right? Because then you can actually directly compare these neural manifolds among different individuals. And so those are kind of the tricks that you would play. And the two examples I just named are pretty much restricted to relatively simple, straightforward behaviors. The monkeys are doing the center outreaching task that Krishna talked about in his outro lecture, exactly the same behavior. We don't really know what happens with more complex behaviors. For example, the full range of motion that you might have in your hand, that may or may not, that result may or may not hold up for more complex behaviors, more naturalistic behaviors. But I think that's the direction we would go in to compare among individuals.
I think.
Yeah, I agree with.
Yeah, please
Sorry.
go ahead. Go.
Yeah, I agree with Francisco and Benny. And also, I think this this problem also relates with the early one we have introduced, how to model a system, because of course, different subjects can be different in any aspects, right? But that depends on what kind of question you are interested in. So, to me, that is more like a model assumption. So, if you assume that this subject variability is independent or not important to your question, then of course you can pull all the data together to do dimensional reduction or other modeling system. Otherwise, your assumption could be wrong. So, it really depends on how you know or how you assume about the system or the question you want to study. Yeah.
I think that's a perfect point, because this is not just something that applies to the linear and the dynamical systems that we've talked about today, but to kind of the whole school, right? The whole program, that if you care about finding a universal kind of like description of something, then you can pool data all together, and that's kind of one way of doing it. But if what you care about is actually understanding individual differences and the heterogeneity across a population or something, then you can completely restructure your question. And so, like, one of my favorite examples of this is, if you'll permit me here, I'm going to go back to yesterday and Bayes' day, because that's my area of expertise. But one of my favorite papers on that does this, or a series of papers that does this, explores not just which cost function in Bayesian Q combination and causal inference framework is the one that describes the population the best. It actually explores the heterogeneity in the best fitting cost function across a population of humans. So they're saying, do people do they take the maximum a posteriori estimate, or do they do model averaging, or do they do model selection, like these types of things? And they look at, some people are fit better by different types of models. And you can do the same thing here, and that's a completely different and completely valid question to ask is, let's fit the standard, two competing accumulators kind of model. Let's fit the amount of inhibition, mutual inhibition between them to the whole population. That's one question. Or to each individual person, that's another question. And it just depends on what you want to ask. That's perfect. My questions keep, my questions keep popping around here. There's a question also about, so are we good here? Yes, you want to move on, sort of? Or do other people have things that they want to say about this before we move on? No? Okay, cool. There's another question, and I can see actually that Bing is typing some answers too, which is great. Thank you. But maybe we can have a chat about this too. If the neural system is noisy, so this question is from Yunhui, if I'm pronouncing that okay. If the neural system is noisy, why can't humans generate true random numbers as shown in the tutorial? And so there's a nice discussion here. But rather than have it only occur in the text, I was wondering if we could talk about this also for the recording and for all the folks who are watching and don't see the chat too. And so some of the answers are about bias and systematic over or under estimation of how long of certain probabilities, like that we're not great at probability guessing in general. So maybe we can talk a little bit about this too. How come humans can't generate true random numbers?
Funnily enough, we just published a paper on motor habits.
Great.
So uh, the short answer is that why would we expect that a biological system would be truly random? Because if it has a particular dendritic structure, and if it has a particular plasticity plasticity path that it has followed, it cannot be all things to all people. In fact, you have the dendritic explosion early on, and that gets pruned. And when you learn something, you learn a good enough solution. It doesn't have to be optimal. And if it works for you, evolution is not teleological. So if it works for you now, you move on and you do learn other things, because there's a huge opportunity cost if you want to perfect any one task. If you want to perfect any one neural or neuromuscular behavior, then you spend all your time becoming a chess grandmaster. You spend all your time training for the Olympics, right? It's very difficult. So I think the question is upside down. I mean, why would you expect that a biological system be truly random? And here the loaded question is noisy. What is noise, and what is the structure of that noise, and etc. So it's a very interesting question, because I think it reflects this bias we have towards thinking of our bodies are, on the one hand, mathematically pure and they can do everything, but in reality, neural systems are there to work well enough to get you fed, out of bed, to get you moving, etc. So this idea of randomness is antithetical to this, I would imagine. And I'll post a link to that other paper on model habits.
So yeah, this also reminds me a story. So when I taught probability and stochastic process, one student asked me that why we need to learn this. You know, this is stochastic, right? Complete random. So what he means is that there's no law behind it. So actually, yeah, neural system is random, is have some noise, but it doesn't mean that it's completely random. It's not, you know, just like toss a coin or thing. There are some laws behind it, like things the tutorial mentioned this, for example, this regression model, right? It depends on the history as well, although it has some disturbance. So that, I think that limits this brain cannot be a good random number generator.
I'd say that too. I mean, maybe there's a reason why we can't actually randomly generate numbers, because we're constantly living in the same like trajectory through space-time. So there's like, if we could be completely independent and separate from our history, then we might be in real trouble. So like, there's always a reason why the noise looks the way that it does. Okay, well, somehow for the first time ever, we are out of questions. So I would like to take this opportunity to say, hey, please, attendees, I cannot believe that you have no questions. Come on. There's no way that there's only a couple of you who have questions. So don't be shy, please. There's no stupid questions. It's totally okay if you don't know the answer to something. So please put them in that Q&A box or put them in the chat. We really want to hear from you. Yeah. We can riff on some of the questions that have been answered already if we'd like to. If there's anything that we'd like to clarify on while we try to get people to kind of get the creative juices flowing. Maybe they're just this everything was totally clear in the tutorials and they're all experts on everything now, and so we don't need to talk about it anymore. But somehow I think that maybe that's not the case. So is there anything that we've talked about so far that you guys would like to expand on?
I see there's another question from Yun Hui. Are there any brain functions can only be explained by nonlinear dynamical system equations?
Yeah, we talked about that a tiny bit, but maybe this is a good one to kind of return to, because the answer was kind of generally like yes and no, but maybe there are cases where a linear systems approach is not appropriate, even if you simplify the system down to kind of like a local area. Are there any cases that you guys know about there where you really can't squish this into a linear box?
Yes, there are many cases like that. And by way of almost reduction ad absurdum answer, people say, well, I can linearize a system. I can get my PCAs or my ICAs, and I can explain 80% of the variance, 90% of the variance, 99% of the variance. And you say, okay, then a linear approximation works. Okay, now, at risk of being inappropriate, imagine that you go to a party and I find someone that looks 97% like my wife, and I go over and give them a kiss. And I'm like, you're 90, 97%, right? And he says, yeah, but actually the difference is in the small percentage that cannot be explained. And so what you mean by this is that a lot of people, I think, are incorrectly thinking that just because you can linearize a system, you can capture all of the system's behavior. However, in control, even when you use a linearization of the system, you're continually recalculating, and then you have a control law and a gain that takes care of any departures. And for example, Emo Todorov and I did an experiment where we had somebody perform a task and then you do PCA on it. But then if you look at the dimensionality of the remainder, the dimensionality was essentially full dimensional. The remainder was full dimensional. So getting back to this question about, is there anything that cannot be explained, anything but nonlinear? Well, it's very difficult in nature to find anything that's fully linear. I would actually challenge someone to find me a situation that's dynamical, that is explained by exclusively a linear dynamical system. That's rare to find. Most of the time, they're nonlinearity. So there is this, again, this misunderstanding that I think Stroga speaks to very well in his book, which is an introductory book. It could be your first book on dynamics, where he says, let's just look at dynamics as a whole. And then for mathematical convenience, to answer a particular question, you could see if you want to linearize it. Sometimes you don't want to linearize the system, right? Or if you just stay with the nonlinear because it's tractable and that answers your question. We should not fear the nonlinear. I don't know if this is along the lines of what you were thinking, especially going to parties and kissing people who look a lot like your friends, but they're not.
Yes, actually, it's a good thing that the brain is nonlinear, which makes our more creative and more complex, right? Think about it, if we just only respond to things linearly, then it's not intelligence. And there are many examples in the brain showing that the brain is nonlinear. For example, from single neuron level, the generation of action potential, you can see that the neuron has to integrate certain amount of input. When it crosses certain threshold, it will generate action potential, and otherwise it just stay maybe some linear or sublinearly. Okay, so that's one example. And also from network level, you also have this up-down states, right? Simply it's nonlinear. And many others, like why you have two eye, right? If you only use one eye to see the world, then you can see one world. But if you use both eyes, the perception is very different from just switch your eye from left to right, right? My eye is too small, sorry. Yeah, so all these indicates that there are many nonlinear phenomena that can only be described by nonlinear systems. But still, sometimes we can linearize it within a very small regime to analyze the behavior of this neuron. That's still a very useful technique. So that's why I guess we made this tutorial to help you guys. understand linear system as a start.
Cool, great. Well, while we were chatting about that, we have a couple more questions that came in, so that's fantastic. So our next most upvoted question here is a philosophical question, going back to what we were talking about before, about like humans not being great at generating random numbers. And so this philosophical question from Zishan is saying, if human decisions are somewhat deterministic and not random, which, okay, is this an argument against free will? And so I think there's a couple of things that we can talk about here. Like, are human decisions deterministic and not random? Yes or no? And if they are, is this an argument against free will? And then we have some follow-up comments saying that the tutorial mentioned that animals are also bad at being random. Are they just as bad as humans, or are humans more or less predictable? And I guess the implication here is, if animals are less random than we are, do they have less free will than we do? Maybe. Who wants to take this one? Come on, we can speculate. Anybody want to talk about free will?
There's so much to speculate. So I'm wondering what would be the useful direction this person would want. I mean, because there's so many ways to answer such a question. Can Zishan Haki kind of tell us where they're coming from? Is it from the epistemological direction, the ontological direction, purely behavioral, psychological, motor? I mean, there's so many ways in which you can answer this, right?
Yeah.
Perceptual.
Let's do that. Let's have Zishan, if you can put in the box as a follow-up of a few more specifics, and we can think about it and we'll come back to you. That would probably be good. But we can come back. It got some traction here, so people wanted to hear the answer.
I see that Jeff Ehrlich said that humans and animals can be trained to be pretty random, which I like. That occurred to me as well, that I think this is it's possible to develop a task where humans and animals are rewarded for being more random. Yes, I think we can learn to be so. So my wild speculation has something to do with the bias of what's actually in the world that we expect. There's a paper that Jeff just linked to. That might be interesting.
Yeah, we can go check that out too. But I think that's a good point. Like, if we can learn to be random, then the relationship between randomness and free will might not be so straightforward. Okay, but we can also come back to this too if we have some more clarification as well. So let's move on then to another question here. Okay, so this is a little bit more of a nuts and bolts question. So we went into philosophy and now we're coming back into something that's a little bit more concrete here. But Chigao is saying, or is asking, can you guys talk more about the dynamic systems in the brain? I'm a bit confused about whether the dynamic can only be determined or explained by temporal change. And I'm not sure whether this means like whether you could have dynamics in another, like without time, or is that kind of what you're asking, Chi? Because I think in order to have a dynamical system, you have to have time in the equation. And maybe that's like part of this question is just a clarification, but maybe Francisco, you don't agree.
Yeah, not necessarily, because you could also have spatial dynamics. For example, if you look at how cells proliferate, or the spirals that you get in in sunflowers and things like that, the fractal patterns that you get with crystallization in a fluid, it's actually a spatial dynamic. It's like looking at a face portrait, but it doesn't really have to, it's not time that drives it. Now, we're mostly used to looking at dynamical systems in time, because we come at it from the mechanical perspective and Newtonian dynamics. But there is all, you could also apply dynamical systems to spatial patterns. So there are two ways to look at this question. And actually, Steve Strogatz has done a lot of work in that. But I think for the purposes of this course, we're thinking of dynamics as time varying, that the x dot is time. In other domains, you can have the x dot be the next location in space. And you get crystallization and things like that. But I think in this particular case, I think you do mean temporal dynamics.
So you're saying that you could have the x dot be, with respect to space in neural systems as well?
No,
or...
in other fields like crystallization.
Right. So in the case of neuroscience and in the brain, it really just needs to be with respect to time.
Usually that's how we think of it, because it's more useful, because neurons fire in time.
Time is an inherent part of the equation.
Then that's
and we live in time.
Yeah.
Right.
Yeah.
I think there's another interpretation. I'm not sure if I'm interpreting this question correctly, but that's another interpretation, which is that we know that things change in time, right? So why don't we just specify as a function of time rather than as x dot equals something, right? Rather as a stepper in time. I don't know if that's what you're asking or not, but that might be what you're asking. If that's what you're asking, I think it's like one way of thinking about it is that these systems don't have infinite memory, right? And so they have some history dependence, and it's usually something that happened immediately before it, and it could have a longer history dependence, which case we have a longer history dependence, but it's not infinite, right? And so somehow there's a functional relationship between what just happened and what's going to happen in the future. And that kind of intuitively makes sense, right? Like the decision that I'm going to make tomorrow is related to what I did today. If I make some bad decisions, I will pay for it later, right? Like we believe in temporal causality to some extent. And see, I brought up the other C word. I'm sorry, it's late.
No, causality happens next week. We're going to talk about it.
So. Okay. So I think that's why like this dynamical systems formulation, this mathematical formulation, is a really nice and convenient one. And so if we are interested in things that change in time, which animals live in time, we change in time, we all grow up and age, then it's just the natural framework for writing things that way.
So then would you say that the specification that was introduced today, where you can actually predict or calculate the current state of the system after X number of time steps, sorry, I won't use X, after some number of time steps, that's really a computational convenience for us as scientists? But that's probably not what the brain is doing. It doesn't have some initial condition and then it's saying like, okay, this is how much time has gone by and this is now the current state of the system. It doesn't remember the initial condition. It really only remembers what happened in, some truncated window of time that happened directly before this. Am I understanding what you're saying correctly?
Yeah, it's definitely, I mean, so I think one of the things that's really interesting about these formulations is that the system, even after a long time, does have some memory of where it started, right? So at least some of the formulations do. So if you start in some orbit, you tend to remain in that orbit. And so the fact that you're here going at its velocity means that you had to have started in some conditions and categorically not in others, right? I think the other thing that another reason that I'm just going to preview to the rest of the week, the reason why we spend so long looking at linear dynamical systems is because it's a really convenient framework for doing control theory, which I know that's something that Francisco brought up earlier as well. And controlling a linear system is particularly well formed. Like we know how to do that, and you can manage a lot of non-linearities by applying inputs, right? Inputs in this case could be like a muscle input. And so you can keep your behavior, you can keep your body in a relatively linear regime by applying constant inputs. And that's a convenient thing to do, right? And that gives you some memory of what happened in the past as well. And so I think a lot of this, like, I'm seeing a lot of questions in the Q&A where I think people are just, there's a lot of different applications of the same piece of mathematics. And the difference is usually in what you define as the state, right? You can do a lot with exactly the same equations. You just have to be smart about what you've defined as a state. So like the same math can define all kinds of things, right? Like there was a question about drift diffusion models and memory, which is something really common. Like, you know, Megan, you say you've worked on that too, and I've worked on it as well. Like lots of people have worked on that type of system, and it doesn't matter what you define as a state.
It's almost like the math is, you know, semantically agnostic. It doesn't care about the content. It really just cares about, like, you can assign whatever semantics you want to the math, and it will answer completely different questions.
Yeah, that's actually the charming of math, just to find the abstract rules to cover lots of phenomena. Yeah.
Yeah, but I think that actually the progression, especially this week, it feels like a very excuse my pun, but kind of linear progression through the through the ideas here. We start with, you know, Bayesian inference, and we go to linear dynamic systems, and then we go into decision making and control and reinforcement learning, and they're all kind of like building on each other in this really interesting way. But also throughout the same math or the same types of math, like you can have a sequential probability ratio test, which looks an awful lot like sequentially applying Bayes' rule. Well, that's kind of what it is. The prior at the posterior at the previous time step becomes the prior at this time step. But the semantic content and like the meaning that you apply within the abstraction can change, and the whole model can change in terms of what it can tell you. Cool. So Chi, I hope that answers your question there. Awesome. Okay, we have time for maybe one or two more here. Let me just orient myself here. We've got some that are answered as well that were kind of answered in the chat. So thanks for doing that. Bing, you're doing my job for me. That's awesome.
Oh, I'm sorry. I feel like there are some of them were just really specific.
No, I think that's great.
And so I just typed in the answer.
I think that's great. And I want to actually highlight that you guys should be able to see these too. So if you switch over to the answered tab, you can see that some of these very specific questions have been answered. And so if you were also one of the people who was curious about those, then go and read the answers, and we can kind of keep the conversation going there, and then move over to NeuroStars after the end of the session. So that's great. Okay, so we've got Lena was talking about the drift diffusion model. I think we kind of covered that just very briefly here, and that we're going to talk a lot more about that, I believe, tomorrow. Yeah, so Lena, hold that thought, and when you wake up in the morning, you'll have all of your answers. But the short answer is yes, it all kind of goes together. And so that's why it's being introduced, you know, sort of in this way. Okay, so we've done that one. So I think actually we're pretty good here. So we can come back to this question. Zishan is saying, just thought it was a fun question and open-ended. But maybe this is where we can kind of wrap up for the session here. This idea of stochasticity and randomness, and whether they have anything to do with each other. And then we can kind of have some parting words that we want to impart some wisdom for the students, and especially people who worked on the tutorials for this week, if you want to say like kind of what to look out for tomorrow. So two alternative force choice. Is free will related to randomness? What do you guys think? Yes, no, go. Terrible question, sorry. But I think, okay, so here's the thing, like the reason that it's hard to answer is that like we don't have enough information to go on to really answer this question. So that's my cheat answer there. Would you guys have anything else to say about that?
Yeah, I guess
I think it depends on if you believe in parallel universes.
Yeah, Binny, go ahead.
Sorry, Songting. I was just being snarky. I was going to answer whether or not it depends on whether or not you believe in parallel universes.
All right. Now we went real philosophical here. Songting, did you have something to add?
Yeah, I saw John left a message say somewhat deterministic or rather random. That's actually very interesting, because in mathematics, you know, you can construct such kind of example. You have a deterministic rule, and actually it has a purely stochastic rule, have one-to-one map between it. So maybe that could be the explanation. You know, we don't know whether free will it originates from this stochasticity or just from deterministic, maybe both, maybe they're equivalent philosophically. Yeah.
Mm-hmm.
But also the question of free will can be asked at different levels. Like, for example, you could be very malleable about what you want to eat. Like, do you want to have the tacos or do you want to have the burger, right? You could have free will, but you have no choice about whether or not you will eat. So you're going to have to eat. If you don't eat, you're going to die. So yeah, some people choose not to eat and die, right? But again, it's a matter of scale. You could say, well, I do have free will. I can choose whatever's on the menu. But the fact is, you're choosing from the menu. So at one level up, you're abiding by some rules. So this is kind of a fun way to for those of you who are coming into breakfast or lunch. As you decide what to eat, you could also decide not to eat, and think out of the box.
Well, that seems like a pretty good place to stop. But before we sign off here, do we have any words of wisdom to shoot off into Wednesday with for everybody? Anything to look out for over the next couple of days, or also anything that in your own research you think is particularly important about these types of systems that we didn't cover this evening?
Yeah, I would just say beware of mathematical convenience. Mathematics is awesome, but we only have one particular mathematics available to us. So we try to, that's all we've got. So we use it, but the brain never took those classes that Songting is teaching, right? So mathematics is a nice metaphor, but the map is not the territory. That's a Zen koan you can think on for the next 2 days. The map is not the territory. Very philosophical.
I like it.
Yeah, a follow-up comment is that we needed to develop new mathematical tools to understand the brain.
Yes, exactly.
Awesome.
I agree with both of those comments, and I think that's actually there was a couple of years ago. I think there was an opinion piece authored by Phil Holmes, who was an applied mathematician, arguing that that in fact the quest of understanding the brain should be one of the new frontiers of mathematics. Like our attempts to try to understand the brain is going to inspire new math to be invented that we didn't know existed before.
Mm-hmm.
I think that's a fantastic place to end, because that's what we're hoping to inspire all of our students to do here at NeuroMesh Academy, is like see the power of what we can do, but also see how limited our current techniques are. And so how much work needs to be done still. Cool. Well, this has been really a pleasure. I want to thank Francisco, Songting, and Bing for their insightful commentary and lending us their brains this evening, especially for a few of us. It's a little bit late. So thanks for staying up. And I think that some of you guys will be back on other panels. Is that right? So we may see you again in the near future, right? Okay. All right. Well, thanks again. Really appreciate it, and hope that all of you out there have a restful evening and wake up ready tomorrow for some more math. So more math. Hooray.
More math.
No, it's always good. Math and brains is always good. So. Yep. All right, guys. Well, thanks again for being part of this, and we'll see you next time.
Bye-bye.
Thank you. Bye.
Thanks for asking questions. Thanks, Megan.
Bye, Megan. Good night.
Bye.
Bye, everyone.